Welcome to This Explainer. Today, we're going to break down the true mechanics of global resource depletion. This isn't just about what we take out of the ground, it's really about the very foundation of modern civilization. So let's just dive right into this fascinating and honestly deeply urgent topic. We're going to unpack the historical trends, the hidden economic engines, and the real-world fallout of our resource development.
To really understand where we're at right now, we have to look at how humanity's relationship with the planet has fundamentally shifted. For most of human history, we lived in a state of primitive dependence. Our resource consumption was strictly bound by organic, real-time biological limits. Think immediate inputs, right? Timber, wind, surface water. But as the research points out here, that relationship has transformed into an aggressive, systematically institutionalized mastery of nature. And let me tell you, that shift changes absolutely everything about how our world operates.
So, here's our roadmap for today. We'll start with the anatomy of resources, trace the great acceleration, uncover the engines of extreme extraction, examine the price of progress, look at social fractures and geopolitics, and finally, confront the thermodynamic conflict.
All right, let's kick things off with Section 1, the anatomy of resources. This is where we define our baseline and the very rules of the game we're playing on this planet.
It's super vital to realize that a resource isn't just a physical object sitting in the dirt waiting for us. Modern resource development actually operates as a highly integrated technological process. Whether we're talking about renewable flows like solar and biomass, or non-renewable geological reserves like hydrocarbons, the speed of extraction isn't just about where the material is located. It's dictated almost entirely by economics, market valuation, capital depth, and automated processing mechanisms. It's a whole system.
Now, here is a really fascinating mathematical cheat code used by resource economists. To measure our absolute footprint, they use this classic iPad framework. Basically, it states that total environmental impact equals population times affluence, which just means per capita material consumption times technology, representing the efficiency or intensity of our extraction methods. So, what does this actually tell us? Well, it brilliantly illustrates that sheer population numbers aren't solely to blame for resource depletion. We often hear that there are simply too many people on Earth. But the math says no. It shows us that it's actually the structural intensity of our consumption, our affluence, and the aggressive technological methods we use to extract materials that exponentially multiply the damage.
Moving right along to Section 2, the Great Acceleration. Let's see how this historical overdrive built into the unprecedented timeline we see today.
You see, our extraction timeline isn't just some steady, gradual climb. It's a nonlinear, compounded acceleration. While early agrarian societies had pretty localized impacts, the industrial shifts of the 18th and 19th centuries actually severed human production from biological cycles by tapping into deep geological carbon. But the true inflection point, that hit right around 1950. This era, universally known as the Great Acceleration, is when global economic outputs, urbanization, and technology all synchronized. They essentially launched an exponential expansion in extraction.
Just look at the sheer velocity of this change over a 50-year window. We're talking about aggregate physical extraction of primary materials skyrocketing from roughly 27 billion metric tons in 1970 to over 92 billion metric tons in 2020. That is absolutely massive. Across the board, from biomass to fossil energy to metals, we're seeing undeniable, massive multipliers in what we pull from the Earth.
But check this out. The crucial point here is this massive 373% spike in non-metallic structural minerals. We're talking things like specialized sand, gravel, and aggregate stone. Why is that specific category completely dwarfing the others? Well, it proves that contemporary resource development is currently locked into feeding massive, heavy concrete infrastructure networks globally. We are literally paving the planet, building the very concrete cities and roads you navigate every single day.
And of course, this material wealth isn't shared equally, right? The data shows a really sharp geographic imbalance. Advanced post-industrial nations consume upwards of 10 times the volume of raw materials per capita compared to developing economic zones. The structural strain is highly concentrated in specific affluent areas of the globe.
So, what exactly is pushing the pedal to the metal here? Let's dive into Section 3, Engines of Extreme Extraction, and uncover these hidden drivers.
These four structural mechanisms act in tandem to constantly reinforce our aggressive global extraction. First, as populations grow and rapidly migrate to urban centers, the demand for heavy infrastructure skyrockets. Second, our macroeconomic frameworks demand endless GDP growth. Third, technology like hydraulic fracturing and automated ocean mapping has drastically lowered the economic barriers to extraction. And fourth, our markets completely fail to price in the environmental damage.
Let's actually look a little closer at that second point. Our cultural and economic obsession with GDP locks our societies into a very strict one-way linear throughput dynamic. It goes extraction to processing to consumption and finally to disposal. Market stability actually relies on planned obsolescence and continuous replacement cycles, treating geological resources as cheap, infinite inputs, and nature as basically an open-ended trash can.
But perhaps the biggest systemic flaw of all lies in how we price things. Classical market mechanisms completely fail to assign real economic value to natural capital. Essential, literal, life-saving ecological functions like the atmosphere absorbing carbon or soil microbiome cycling nutrients are treated as free, unpriced externalities. Because the long-term cost of resource depletion is left off the balance sheet, extraction stays artificially cheap, which actively incentivizes overexploitation.
And when you treat nature as an unpriced input, the systemic strain inevitably catches up. That brings us to Section 4, the price of progress and the resulting environmental fallout.
This unmitigated expansion doesn't just happen in a vacuum. It physically damages the biosphere's architectures. And it's not just carbon emissions. It's a cascading web. The intensive thermal combustion of subterranean fossil fuels is pumping immense volumes of CO2 and methane into the air, driving ocean acidification and extreme climate anomalies. Broad-scale open mining and clear-cutting trigger habitat fragmentation, crashing global wildlife biomass. And massive water extractions combined with chemical agriculture are actively destroying deep aquifers and soil microbiology, leading to vast desertification. It's like a giant puzzle where every piece affects the others. These are deeply interconnected vulnerabilities.
And, as you might guess, this environmental disruption directly fuels our next topic. Welcome to Section 5, Social Fractures and Geopolitics.
Now, this is a deeply counterintuitive academic concept. You'd think that sitting on a gold mine or a massive oil reserve would make a nation universally wealthy and stable, right? But the resource curse reveals the exact opposite. Massive natural endowments in developing areas frequently lead to institutional corruption, currency distortions, and civil unrest. Why? Well, because the state apparatus becomes entirely focused on capturing resource rents for the elite rather than developing comprehensive socioeconomic institutions for the actual people.
Ultimately, it's local and marginalized groups that consistently experience the toxic downside of this global dynamic. Hazardous tailing pond leaks, heavy metal pollution, and outright geographic displacements occur overwhelmingly near vulnerable populations. This structural inequality forces immense toxic burdens onto those who are quite literally least equipped to handle them, driving fierce geopolitical resource friction all across the globe.
Which leads us to our final section, Section 6, the thermodynamic conflict. Let's look at the ultimate, inescapable limit governing our civilization's future.
Our industrial economics treat the Earth as an infinite open loop of material input and output. We act as if there's always going to be another frontier. But thermodynamics, the actual laws of physics, dictate that accelerating raw material throughput within a closed planetary system inevitably drives up systemic entropy. In plain terms, you literally cannot endlessly accelerate extraction in a closed box without generating massive localized instability and global environmental degradation. It's just science.
So, I'm going to leave you with this provocative thought to ponder. We've seen the mechanics, the acceleration, and the fallout. As our material velocity continues to compound, driven by systems that demand endless growth, how long can our economic structures ignore the physical, finite limits of the very resources that built them? Thank you so much for joining me for this explainer, and keep questioning the structures around you.